All right, in this video, we're going to talk about section 3C, and it's titled Dealing with Uncertainty. And in this section, we're going to discuss ways of dealing with the inevitable uncertainty of numbers when we encounter these in daily life. All right, so the first thing I'll talk about is significant digits here. Now, the significant digits of a number are the digits that have meaning or contribute to the value of a number. Sometimes we call them significant figures. Okay. Now, the table that you're going to see on the first page of your handout will tell you which digits are going to be significant. Okay, and here it is. All right, here we have the type of digit and its significance for those digits. All of your non-zero digits will always be significant. That's the ones from 1 through 9. All non-zero numbers are going to be significant. All right, next, zeros that follow a non-zero digit and lie to the right of the decimal point are always significant. Like in 4.20, this zero is significant. And in 3.00, those two zeros are significant. Okay? Anytime you have zeros between non-zero digits or other significant zeros are significant. Like in 4002, the two zeros in between are significant. And in 3.06, that zero after the decimal point and in between those two non-zero numbers are significant. And then you have other significant zeros, such as the first zero in 30.0. That too is significant. What's never significant will be zeros to the left of the first non-zero digit. So like in the number 0.006, these zeros in front will never be significant. And in 0.00052, these zeros in front of the 5 are not going to be significant. So those zeros that are to the left of the first non-zero digit will never be significant. And then we have zeros to the right of the last non-zero digit, but before the decimal point, as in 40,000 or in 210. Those are not significant unless stated otherwise. So in this case here, if you don't see a decimal point in a whole number like 40,000, those zeros are not going to be significant. 210 doesn't have a decimal point behind the last zero. That zero there will not be significant. Okay. So now let's look at some examples of significant digits. Like in this case right here. Here I want to state the number of significant digits and the implied precision of the given number, like in the number $2,502 per acre. Okay? So we want to state the number of significant digits here. Here I got a zero in between two non-zero digits. That is considered to be significant, along with the other non-zero digits. So the 2, the 5, the 0, and the 2 are significant. So that means I have 4 significant digits in that number. And let's see how precise this number is. Okay, so it is going to be precise to the nearest. Well, it is a whole number, so that means this is going to be to the ones place, and we're dealing with money amounts here. So here, this number will be precise to the nearest dollar per acre. So that number is precise to the nearest dollar per acre. All right, in example 2, the number 10. We want to find out how many significant digits there are and its implied precision of that number. Well, Look at the number 10. We know the 1 is significant, but the 0 is not, because there's no decimal point behind it. Because the rule says here, zeros to the right of the last non-zero digit, but before the decimal point, as in those numbers I gave you, they're not significant unless otherwise stated. So here, you only have one significant digit. And this is going to be precise to the nearest. Well, the only significant digit is a 1. That 1 is in the tens place. So this number is precise to the nearest tens place. All right, number 3, or example 3. State the number of significant digits and the implied precision of the given number for 1.81241 miles. Well, notice in this case here, all of the digits that you see in this decimal are significant because they're all non-zero digits. So that means if you count the number of digits in that number, there are 6 significant digits. 6 significant digits. And we need the implied precision. Well, in this case, it's going to be precise to the nearest. And we're going to look at the last place value position of the last significant number. So here's a decimal point. This will be tens, hundreds, thousands, 10,000s, 100,000s. This last one is in the 100,000s place. So it's precise to the nearest 100,000th of a mile. Because the unit that we're using here in this example is miles. All right, example 4. All right, we got 179.7267 pounds. Let's find out how many significant digits there are. In this case here, there's 1, 2, 3, 4, 5, 6, 7 significant digits because these numbers are all non-zero digits. They are significant. So there's 7 significant digits here. Let's find out how precise this number is. So in this case here, it's going to be precise to the nearest. Well, let's look at the last digit, last place value position for this final digit. That's the tens, hundreds, thousands, 10,000. So it's precise to the nearest 10,000 of a mile. Not of a mile, of a pound. In that problem here says pounds. Okay. And number 5. We got 52.22 kilometers per second. Let's count the number of significant digits that we have here. These are all non-zero digits here. They're significant. So there's 1, 2, 3, 4 significant digits in that number. And then we want to find out the precision of that. It is precise to the nearest. Well, take a look. This last 2 is in the hundreds place. That's the second digit after the decimal point. So it's precise to the nearest 100th of a kilometer per second. And I'm abbreviating kilometers per second. Now for the implied precision, you'll be given a choice of answers there. And all you have to do is select the one that will best fit that particular problem. Okay, so that's how we count the number of significant digits in a number. All right, now let's talk about how to round with significant digits, rounding with significant digits. Now for adding and subtracting, you first do the calculation and then you're going to round your answer to the same number of decimal places or places to the right of the decimal point as the number in the calculation with the fewest decimal places. Now for multiplication and division, to determine the number of significant digits in your final answer, you're going to multiply or divide. In other words, you're going to do the calculation first, and then you're going to round your answer to the same number of significant digits that is in the number with the least number of significant digits in your calculation. Okay. Now let's look at these next two examples, example 6 and 7. All right, in this example, you're going to carry out the indicated operation and give your answer with the specified number of significant digits. Here, we got 42 times 32.4, and we want our answer to 3 significant digits. Okay, so we're going to use our calculator to do 42 times 32.4. And we're going to get the exact answer of 1,360.8. Now it does say give our answer to 3 significant digits, as indicated here. Let's count significant digits from left to right. 3 significant digits. 1, 2, 3 significant digits. That's going to be the third number from left to right, or the third non-zero number from left to right. That's going to be the 6. To the right of it is 0, so that's less than 5. So this 6 remains the same. So this will be approximately 1360. And that's without the decimal point. So it'll be 1,360 for our answer rounded to 3 significant digits. Okay. All right, example 7, same thing. We got 241.41 divided by 0.073. And we'll want this answer to 2 significant digits. 2 significant digits. So let's see. I'm sorry, 241.41 divided by 0.073. Well, the exact answer would be 3,306.986301. I'll go ahead and copy that down. Okay, and I'll show you again. All right, now we want this to 2 significant digits here. So going from left to right, here's 1 and here's 2. The second 3 is in the hundreds place. To the right of that is a 0. Again, that's less than 5, so we're going to leave this second 3 as it is. So it'll be 33 with 2 zeros and no decimal point, because it has to be the 2 significant digits. So our final answer there to 2 significant digits would be 3,300. All right. Now let's say your numbers are in scientific notation. Here you're going to disregard the power of 10 and use the rules for significant digits on the decimal number only. So in this case, you're going to carry out the indicated operations and give your answer with the specified number of significant digits. So here we got 1.65 times 10 cubed times 7.8 times 10 to the negative 2. And we want this to 3 significant digits. So I'll go ahead and write this out, 1.65 times 10 cubed times 7.8 times 10 to the negative 2. And if you remember, when we multiply scientific notation, we multiply the numbers that are in front of the powers of 10. Group those together, that'd be 1.65 times 7.8, and then times, and then we group our powers of 10, 10 to the third times 10 to the negative 2. So in this case here, if I do 1.65 times 7.8, that would give me 12.87. And then when we multiply powers of 10, we bring the base over, which is our 10, and then add the exponent. So this will be 3 plus negative 2, which will be 1. So I have 12.87 times 10 to the negative 2. But this part, it says 3 significant digits, so I need to give this part right here to 3 significant digits. So here's the first, second, and then the third significant digit here is an 8. The digit to the right of that is a 7. That's bigger than 5. So this 8 increases to a 9. So it'd be 12.9 times 10 to the first. Now, if you remember, scientific notation is a number that the first part has to be at least 1, but less than 10, multiplied by a power of 10. We need to write 12.9 in scientific notation because this is bigger than 10. So in this case here, I need to put the decimal point behind the 1. So it will be here. So here I got 1.29. So here I have to move this decimal point only one place to the left. So it'll be 1.29 times 10 to the 1. And then I got this other 10 to the first power. I need to bring that down as well. Now, when you multiply powers of 10, bring that base over, add your exponent. So 1 plus 1 will be 2. So in scientific notation, in the correct scientific notation, this will end up being 1.29 times 10 to the second power to 3 significant digits. All right, let's talk about understanding errors. Now here we're ready to deal with errors themselves, and we will describe 2 types of errors. Discuss how to quantify the sizes of errors and how to report final results to account for errors. Now here there are 2 types of measurement errors. One of them is, of course, random errors. They occur because of random and inherently unpredictable events in the measurement process. And then you have systematic errors. Those occur when there is a problem in the measurement system that affects all measurements in the same way, such as making them all too low or too high by the same amount. All right, now if you look at the next page, this is just an illustration of what a random error is and what a systematic error is. On the left-hand side, if you look at the scale, you have this. The baby's motion makes the scale readings jump around randomly. And this is where you have random errors, okay? And as you can see in this illustration here, you see just numbers all over the place. So in this case here, because the baby's moving around, so you're not going to get an exact weight of this baby. So, and that's where random errors happen. Now on the right-hand side, the scale, as you can see, there's nothing on that scale. It reads 1.2 pounds even when empty. This introduces an error in the measurement system called a systematic error. And that will make all measurements 1.2 pounds too high, okay? Because someone did not, I don't know what they do. They have to calibrate the scale for it to be at 0, okay? So in this case here, it's starting off as 1.2 pounds. All right, now let's look at size of errors. Now, in one of the videos, we did talk about absolute and relative. Well, we're introducing this as absolute error and relative error. The absolute error describes how far a measure or claimed value lies from the true value. So the absolute error is just subtracting the measured value minus the true value. So it's just a simple subtraction. However, for the relative error, the relative error compares the size of the error to the true value. And here's how we calculate the relative error. That's going to be the absolute error divided by the true value. Or since the absolute error is this, we can say that the relative error will be the measured value minus the true value divided by the true value, and then multiplied by 100%. Because, of course, we'll be looking for a percent. I'm sure in the homework they're going to ask for you to give the answer as a percent. All right, so now let's look at an example of this, or a few examples of this. Here we're going to find the absolute and relative errors in the following situation. Your true weight is 68.0 inches or 5 feet 8 inches, but a nurse in your doctor's office measures your height as 67.6 inches. Okay. So here, we're going to find the absolute error. And of course, the absolute error is always going to be the measured error. Minus the true error. I'm sorry, not measured error. It's actually the measured value minus the true value. Okay. The measured value minus the true value. Now, of course, the measured value was 67.6 inches because the doctor's office measures your height at 67.6 inches. That's the measured value. Let's subtract from that the true value. Your true height was 68.0 inches. All right. So if we do 67.6 minus 68.0, you're going to end up with a negative value of 0.4. So it'd be negative 0.4. That's the absolute error. And now let's find the relative error. And for finding the relative error, that's going to be, I'll write this out, the measured value minus the true value, all divided by the true value times 100%. And in this case here, your measured value minus the true value, we can get that from up here to get the absolute error. That was negative 0.4. So the negative 0.4 divided by the true value. In this case, your true value was 68.0. That goes in the denominator. That's multiplied by 100%. And using our calculator, this will be negative 0.4 divided by 68.0 times 100. And let's say they want to round this answer off to the nearest tenth or to one decimal place. Okay, to the nearest tenth or to the nearest to one decimal place. And in this case, this will be that 8 will increase that 5 to a 6. So it'd be negative 0.6%. So the relative error there will be negative 0.6%. Okay, example 10. Again, we're going to find the absolute and relative errors for this situation. Your bike's speedometer reads 28 miles per hour when you are actually traveling 26 miles per hour. Okay. And in this case, I want to find the absolute error and then the relative error. Absolute error is going to be this, the measured value minus the true value. Here's the measured value right here, 28 miles per hour. And this is the true value, or the true speed, 26 miles per hour. So it's the absolute minus the true, 28 minus 26. I mean, the measured minus the true value, 28 minus 26. That's going to give us 2. And then we want the relative error. Well, the relative error will be found by taking the absolute error, which is 2, divide that by the true value. You're actually driving 26 miles per hour. That's the true value there. So it'll be 2 divided by 26 times 100%. So 2 divided by 26 times 100. To one decimal place, it'll be 7.7%. So the relative error there will be 7.7%. Okay. And example 11 is this. You measure the length of a flower garden to be 10 3-foot paces. A tape measure gives the actual length of 28.5 inches. All right, now we need to take 10 3-foot paces. So that 10 represents 10 paces. 3-foot paces means 3 foot for 1 pace. So that's 3 feet per 1 pace. So here we have to do unit analysis here to convert this to feet. Here, paces divide out. 10 times 3 will be 30 feet. So we measure a flower garden is 30 feet. But a tape measure gives the actual length of 28.5 feet. So let's find the absolute error. That will be, in this case here, the measured value minus the true value. The measured was 30 feet. Minus the true value, which was 28.5 feet. So if I subtract 28.5 from 30, that's going to be 1.5 feet. So the absolute error there will be 1.5 feet. Now let's find the relative error. That's going to be that absolute error of 1.5 divided by the true value, of 28.5 feet times 100%. So if I do 1.5 divided by 28.5 times 100. Let's see, to one decimal place, this will be approximately 5.3%. So the relative error there will be 5.3%. Okay. So that's how we find the absolute error and then the relative error. All right, let's describe results. Two key ideas about any reported value are its accuracy and precision. Although these terms are often used interchangeably in English, they're not the same thing. They're different. Accuracy describes how close a measurement approximates a true value. An accurate measurement has a small relative error. But precision describes the amount of detail in that measurement. Okay. So if you see so many decimal places numbers after the decimal point, that tells you they're using precision there because they're trying to get a precise number. That's the amount of detail in a measurement. Okay, so in this example, number 12 on the next page, explains this. For a pair of measurements, state which one is more accurate and which one is more precise. And you're given a choice of answers for this one. Your true height is 67.40 inches. A tape measure that can read to the nearest 1/16th of an inch gives your height as 67 1/16 inches. A new laser device at the doctor's office that gives readings to the nearest 0.2 inch gives your height at 65.8 inches. And then you want to choose your correct answer. In part A, it says that the laser device is both more accurate and more precise. The tape measure is more accurate and the laser device is more precise. The tape measure is both more accurate and more precise. And then the laser device is more accurate and the tape measure is more precise. Well, a tape measure measuring 1/16 of an inch gives us 67 1/16 of an inch. But then you got that laser device that gives readings to the nearest 0.2 inches. If I do this, if I do 1 divided by 16, as a decimal, this will be 0.0625. That tape measure would be more precise than that laser reading or that laser device that they're using. Okay? Because a laser device is accurate to only like 0.2 inch. The tape measure is more accurate or more precise to like 0.0625. So I would think that the tape measure would be more accurate and not only that, more precise. More accurate because the difference between your true height and the height that's given by that laser device is very large, by about 1.6 inches. The tape measure compared to your true height would be closer to that because that's like 67, and I'm gonna add the plus 67 to that. That's like 67.0625, and you got 67.40. That's closer by point, I'd say 3.375. Okay, So here it's more accurate, and not only that, it's more precise for the tape measure. So I would choose that answer here. Okay. All right, and finally, we'll talk about combining measured numbers. The rounding rule for addition or subtraction is this: you're going to round the answer to the same precision as the least precise number in the problem. Now, for multiplication and division, you're going to round the answer to the same number of significant digits and as the measurement with the fewest significant digits. And to avoid errors, round only after completing all the operations, not during the intermediate steps. So that means you just want to do add or subtract or multiply or divide as you normally do. And then whatever answer you get for that, you will round only. You'll do your rounding. Like in this example here. If I can bring this up. Here we go. Use the appropriate rounding rules to do the following calculation. And you're going to express the result with the correct precision or correct number of significant digits. Like we're going to add 0.2 pounds to 136 pounds to find your weight before you went for a run. So we got 136 pounds. We're going to add 0.2 pounds. And you can do this on the calculator. You're going to end up with 136.2 pounds. Okay. Now, we want the fewest number of significant digits here. We want the same precision as the least precise number in the problem. Here, 136 is the least precise number. So we're going to round to the nearest whole number. That 6 is the number in front of the decimal point. That's the ones place. To the right of it is 2. That 2 is less than 5, so the 6 remains the same. So this will end up being approximately 136 pounds. 136 pounds. So the weight before you went for a run is 136 pounds. All right. And on the last page is examples 14 and 15. We're going to divide 107 miles by 60.69 hours. 107 miles divided by 0.69 hours. So 107 divided by 0.69. Here I get 155.0724638. So let me go and write that whole thing out. 155.0724638. Now, with division, we round to the same number of significant digits as a measurement with the fewest significant digits. In this case here, we're going to round to, in this case, the 3 significant digits here in that problem. So, actually, we're going to round to 2, because this one has 3 significant digits in the number 107. Where in 0.69, there's only 2. So 155 will be rounded to 2 significant digits. So here's the first and here's the second significant digit. That's a 5. To the right of that is a 5. That's 5 or greater. This 5 increases to a 6. So it'll be 160. And this will be in miles per hour. So if you are to answer that question correctly, that will mean that your speed would be 160 miles per hour, approximately, to 2 significant digits. And finally, example 15. Her birth weight 6 pounds, 15 ounces. Your baby adds 15.2 ounces. What is her new weight in ounces? Well, the fact is we need to convert 6 pounds, 15 ounces to ounces. I know that 1 pound is equivalent to 16 ounces. So for 6 pounds, we need to multiply that by 16 ounces. The 16 ounces is equivalent to 1 pound using unit analysis. And here you see the pounds divides out. 6 times 16 would be 96. So you have 96 ounces. But we got the 15 ounces there, so 96 ounces plus 16 ounces. 15 ounces. Okay, in case you see that, 15 ounces. 96 ounces plus 15 ounces is 111 ounces. Okay. Now we're going to add that to the 15.2 ounces. So 111 ounces plus 15.2 ounces gives us 126.2 ounces. Now, in this case here, 111 ounces has three significant digits. 15.2 ounces has also three significant digits. So we're going to round our final answer to three significant digits here. Okay, 1, 2, 3 significant digits. This 6 is the third significant digit. To the right of that is 2. That's less than 5, so we leave the 6 as is. So this will be approximately 126 ounces, rounded to 3 significant digits. Okay. All right, so that does conclude this video on section 3C, titled Dealing with Uncertainty. Please feel free to reach out to me if you have any questions about any of the examples presented in this video or any of the homework problems on section 3C.